Today on part 221, we'll be discussing Pearson's correlation coefficient. Coefficient correlation refers to the ratio of covariance between the related variable to the square root of the product of individual variances. At the end of this lecture, you should be able to explain the Pearson's correlation coefficient, describe the computation of linear correlation coefficient, and to apply the concept of correlations in administration and business decisions. Pearson's correlation coefficient is denoted by the symbol R. It is a statistical measure that quantifies the linear relationship between two continuous variables. It is one of the most widely used methods of calculating correlation between variables. It ranges from -1 to +1, and as discussed in our previous session, +1 indicates perfect positive correlation, which means the two variables are increasing proportionally. -1 indicates a perfect negative correlation, which means as one variable is increasing, the other variable is decreasing proportionally. When R is equal to 0, it indicates that there is no correlation between the two variables. There is no linear relationship between them. The formula for calculating the Pearson's correlation coefficient is given as follows. There are two alternatives to this formula. You either go with the first one or the second one. So going by these formulas, x and y are individual data points of variables x and variable y. The x and y's in the formula are individual data points of the variables x and y respectively, where x bar is the mean of the x values and y bar is the mean of the y values respectively. Pearson's correlation coefficient is sensitive to outliers and assumes a linear relationship between the variables. Thus, even though there is no linear relationship, when outliers are present in a data set, the Pearson's correlation coefficient tends to assume there is a linear relationship because the outliers affect the result of a Pearson's correlation coefficient. And what do I mean by outlier? An outlier is a data point that differs significantly from other data points in a data set. Such data points affect the computation of the Pearson's correlation coefficient. If we have a data set comprising of 10 values of, let's say, 2, 4, 6, 8, 10, 12, 14, up to 20, and then all of a sudden another value reads 100, another value reads 1000. From all the indication, the 246 are most likely to be categorized in the same range, but going as far as 100 or 1000 in the same data makes that 100 or 1000 an outlier, because it differs significantly from the rest of the data points. That's what an outlier means. If the relationship between the variable is not linear, or if outliers are present in the data, other correlation measures are more appropriate, such as the Spearman's rank correlation and the Candel's correlation approaches. Pearson's correlation coefficient is widely used in various fields, including science, social science, economics, and finance. Excuse me. To understand the strength and the direction of the relationship between two continuous variables. The value of R is expressed in three ways, which interprets the relationship between x and y. It's either +1, which is perfect linear relationship. It's either -1, which is perfect linear negative linear relationship. It's either a 0, which indicates no relationship. Here is a numerical example. It says to compute and interpret the correlation coefficient for the following data on 5 students' continuous assessment tests in mathematics and physics. Let's say our mathematics is X and our physics is Y. So going by this course already given, we use the formula as we stated above to solve this particular problem. First off, we start by computing the means of x and y. It's easier when you compute one after the other the segments of the entire formula, so that when you have values from these computations, you just substitute them into the formula itself. So getting the mean of x as 6 and the mean of y as 8, as we all know, the mean of x is summation of all x divided by n. Likewise y. To make it more organized and simpler, this table shows the computation of the individual segments of our formula. On this column, we have our x minus x bar. On this column, we have our y minus y bar. On this column, we have the multiples of, we multiply x minus x bar by y minus y bar. And in this other column we have x minus x bar all squared, and then y minus y bar all squared. Computing this and getting their summations, we are halfway there. What's left now is to substitute the summations into the Pearson's correlation formula. So going by the first alternative of formulae, from our table, we could see that summation x minus x bar, x minus x bar, and let's take that again. The multiplication of summation of x minus x bar times y minus y bar. Going back to our table, x minus x bar multiplied by y minus y bar. This is the column to consider. The summation is what we need. So the summation is 8. That's why we have 8 as the numerator. Considering the denominator, it is the summation of x minus x bar all squared multiplied by the summation of y minus y bar all squared. Revisiting our table, x minus x bar all squared, the summation of that is 20, while the summation of y minus y bar all squared is 6. So that gave us 20 times 6, and then computing this with your calculator, you're going to arrive at 0.7303. Alternatively, using the second formula, the solution will be in this form. Computing the individual segments in the formula, which is y, xy, x squared, and y squared, and getting their summations. This will help us to just substitute these summations into the formula. But I'll be leaving you to do that. I've done half of the task for you, getting the summations already. What's left now is for you to substitute this into the alternative formula as provided when I introduced the Pearson's correlation coefficient. You are either using this formula or the other one. Now I have used this formula to arrive at this answer. I expect you to use the alternative formula, substituting these values into it to arrive at the same answer. If you don't arrive at this very answer, it means there's something wrong with your calculation. So you have to check again. So in conclusion, interpreting the relationship between x and y based on the r value we have. Our r value says we have 0.7303. You agree with me that mathematically this is approximately 1. You could approximate this to 1, and it is positive, not negative. It's not minus 0.73, it is 0.73. That's a positive r value. And so this indicates that there is a strong positive relationship between variables x and y. This wraps up our discussion on correlation analysis. Thank you.